Hello. So far, we discussed about the optimal filter configurations, which are referred to with the Wiener filters. Over there, what we have seen is, if you want to get the optimum filter coefficients, it is necessary that you have to make a lot of calculations. So the calculations are autocorrelation operation, inverse of the autocorrelation operation, cross correlation, and the product of those two cross correlations, and the inverse of the autocorrelation. So these are the things which are involved in obtaining the optimum filter coefficients. It's a very tedious process. And of course, it's possible for us to make these calculations if the signal is stationary, which means that it does not change with respect to time. As long as a signal is stationary, we do have the constant values and we are able to make calculations. But in practice, these signals are also changing with respect to time, and hence it may not be possible for us to perform autocorrelation or cross correlation or inverse of the cross correlation and then find the optimal filter coefficients. And hence, there is a need for a system to adapt itself for the changes that would occur in the input. So this adoption is basically employed by making use of an algorithm called the least mean squares algorithm, which is normally known as LMS algorithm. Sometimes this is also referred to be Windrow algorithm. Of course, the notion of this algorithm is, or it makes use of a concept called steepest descent technique, which means that it's the same concept as that of the bowl surface that we used in case of optimal filters. If you look at that, you have a bowl surface, you have to slide down the surface, reach the bottom of the bowl in order to get the optimum filter coefficients. Instead of that, what we do is we keep calculating the filter coefficients every step we slide down. Every step we slide down, we make the calculations by making use of the previous filter coefficient value, or we make use of the present filter coefficient value and then calculate the next filter coefficient value when you slide down the surface of the surface of the bowl, which is obtained from the mean square error. Now the logic has been represented in the form of an equation here. So this is basically the equation that represents the explanation that I gave now. W is basically the filter coefficient. Wn is basically the filter coefficient at the current instant. Wn plus 1 is basically the filter coefficient in the next instant. G is basically the gradient operation. V is basically certain scalar factor to decide on how fast we have to slide down, and negative sign indicates that is a negative slope because we are not climbing up, we are climbing down, is a sliding down, and hence is a negative slope. So the filter coefficient in the next instant is equal to filter coefficient in the current instant plus the rate at which is laid down multiplied by the gradient value. So this is basically the equation which is used. This V is basically considered to be the convergence constant that governs the rate of descent to the bottom of the bowl. Larger the value of V, will be sliding down fast. The term minus G, as I explained earlier, represents the next square error. Mean square error is nothing but expectation of the square of the error signal with reference to W. In practice, we estimate G instead of using the equations that we had discussed earlier. We estimate it. This estimation is basically referred to be withdraw's estimation for G. So G cap is the estimated value of G. Gradient of square of the error signal with reference to the filter coefficient. I am using Wn to indicate that is a filter coefficient which is a function of time. It is not the first value, second value. Every value is a function of time and hence a subscript n is coming into picture. Whereas in case of optimal filter coefficients, we did not have the subscript n, it was just W. So please note that the subscript n indicates that it's a function of time. So this is approximated to be, that is gradient of the square of the error signal is approximated to be equal to 2 times the error signal multiplied by gradient of the error signal. This is the approximation which has been incorporated. This means that the true gradient is approximated by an instantaneous gradient J. Thus, the steepest descent relation becomes, which is nothing but the least mean square LMS, least mean square algorithm turns out to be Wn plus 1 being equal to Wn minus 2 times Vt, that is 2 times V, this 2 coming into picture because of this V E of n gradient of E of n. This is basically obtained by making the substitution for G in the LMS algorithm that we indicated earlier. Now let's concentrate on the actual configurations. That is, earlier we discussed 3 different configurations: predictor, filter and noise canceller. These are the 3 configurations that we saw. Let's try to transform these configurations into the adaptive filtering configurations. So if you compare this with the predictor configuration, not predictor, filter configuration, we did not have this particular arrow. This arrow was not there. It was just YFN, XFN filter and then error signal. Since the filter coefficients are changing with respect to time based on this particular equation, we indicate this to be with an arrow. Please note that these coefficients are changing with respect to error signal that we have here, and hence error signal is fed back. So we have the error signal is YFN minus GFN, which is nothing but WN transpose XN or XN transpose W. Therefore YFN minus GFN turns out to be this equation. XN transpose is basically this, which we already seen, is the delayed elements of the delayed sequences. So if you make use of LMS algorithm that we have here, it is necessary that we have to evaluate this is a gradient of the error signal with respect to the filter coefficients. I have this as the error signal. If you perform the gradient operation of this on the error signal, what we see is, I'll just concentrate on this first equation itself. So it's nothing but this is independent of W and hence the gradient of this is 0. Gradient of this is nothing but minus xn. So you just substitute in this. Therefore, adaptive filter configuration becomes Wn plus 1 being equal to Wn plus. If you look at this, turns out to be plus because of the fact that this is negative and I have a negative sign here. 2 times V E of n and this is nothing but xn. So minus of minus has become plus. So I can write this as Wn plus 1 plus Wn plus 1 being equal to Wn plus this 2 into V is considered to be V is again a constant, so error signal into xn. So I can make use of this particular equation to obtain the filter coefficient. Please note that this particular equation is in the vector form because the fact that wn plus 1, wn, xn, all these things are vectors, and hence you will have m number of filter coefficients obtained from this particular equation, and hence it is referred to be the vector form. Please note that this 2 times v being equal to v is nothing but a convergence parameter. If the signal is stationary, you can make use of the equation for the optimum filter coefficients. It's basically Sx inverse and Byxs. You'll be able to get the same filter coefficients from this predictor, so adaptive filter configuration also, if the value of V is selected between 0 and 2 by lambda max, where this lambda max is the largest eigenvalue of the autocorrelation matrix Sxx. So the previous equation that we saw is basically the vector form. I can also represent it to be the scalar form. In this case, you'll be evaluating every element based on the every value that you're going to have. So Wi of n plus 1, it can be W naught of n plus 1 or W1 of n plus 1, W2 of n plus 1, which means that I ranges from 0 to m. That is the number of coefficients that we have. W of I of n plus 1 is equal to the filter coefficient, and the same filter coefficient at the current instant. So Wi of n plus V into E of n x of n minus I. We have already seen V into E of n xn. This xn is basically x of n minus I. Right? I can have the values from 0 to m, where this E of n is Y of n into G of n. That is the error signal. So the structure is the same as a filter configuration. Only thing is we are providing a feedback to these filter coefficients which would change with respect to time. This is about the filter configuration, adaptive filter configuration. The same logic can be adopted or applied to other two configurations also. So this is adaptive predictor configuration, wherein you have the signal x of n delayed by a sample duration and then applied to a filter and then subtracted by x of n to get the error signal. Since the filter coefficients are changing with respect to time, this is the fed back to the filter itself and indicating that Wn changes with respect to n. So you have the error signal, this x of n minus g of n. G of n is nothing but Wn transpose xn. We already seen that. So I am using the same equation. Now I have to make use of the LMS algorithm. In the LMS algorithm, we have the gradient of the error signal. So gradient of this error signal is nothing but minus xn, because gradient of this is 0 because it is independent of W. Gradient of this is nothing but minus xn. So if you substitute that value, this is the equation that you are going to have. Wn plus 1 and Wn plus V into E of n xn is absolutely same as the same equation, the equation that we had in case of filter configuration. There is no change in that, except for the fact that xn is a vector which has the elements x of n minus delta, x of n minus delta, n minus 1, etc. And thus 2 times V is represented to be V, which is nothing but the convergence parameter. So the equation that we have here is in the vector form. If I want it in the scalar form, this Wi of n plus 1 being into Wi of n, V, E of n, this xn being replaced by x of n minus delta minus I, where I can have the values from 0 to n minus 1. Right? So if the input is stationary and the xn is assumed to be uncorrelated over time, then the expected value of Wn in the LMS algorithm equation converges to W star Sx star Pxx, provided V is chosen to lie in the range 0 to lambda 2 by lambda max. So whatever the value that you get from this equation, the same value can be obtained from this or from this equation if the value of V that we have here is selected in this range, where lambda max is the largest eigenvalue of Sxx. This is about the adaptive predictor configuration. These are the equations that we use to find the filter coefficients. The last, of course, the structure remains as it is. Only the difference that you see here is the error signal is fed back and indicating that the filter coefficients are changing with respect to time. Rest of the things remain. And the last configuration is adaptive noise canceller configuration. You have the same configuration except for the fact that you have a variable indication here. This is the error signal. You have to obtain the gradient of the error signal, which is nothing but derivative of this is 0, derivative of this is 0, derivative of this is minus V2n. Right? Therefore, the adaptive adaptive LMS algorithm for the adaptive noise canceller configuration happens to be Wn plus 1 equal to Wn plus 2 times Ven V2n. This equation is same as the previous equation that we saw. So here we have V2, there we have X. X was the input to W, that is the filter, and here V2 is the input to the filter. That's all the change that we have. But it's always with reference to the input to the filter. And in scalar form, Wi of n plus 1, this is in the vector form. I can represent in the scalar form by this equation. Instead of V2n, I can put it as V2 of n minus I, where I can have the values from 0 to m, because of the fact that this filter has m plus 1 number of filter coefficients. Right? As in earlier cases, this value matches with the optimum values that you do obtain in the predictor configurations if the value of V is selected between 0 and 2 by lambda max, where lambda max is the largest eigenvalue that exists in the autocorrelation SV2 V2, and the structure remains this. So the only change that you see here is this, that is the error signal has been fed back to the filters where the filter coefficients are changing. Now this is about the adaptive filtering. So far with the 3 videos we have understood, we discussed some introductory part of the adaptive filters and then matrix operations. In the second video we saw the discussion on the different types of configurations that you can think of with reference to the optimum filters, which makes use of FAR filters only. And then in the third presentation or third video, we have seen how those optimum filter configurations can be transformed into adaptive filter configurations by making use of LMS algorithm. So with this we conclude the adaptive filter discussions. Thank you.